the last date of the lecture. So I take this opportunity to thank Sunil from our institute that he has agreed to give this set of lectures. And I also should thank all the participants. I mean, although it has exponentially decreased, but still there are hardcore guys. And the last day participants is actually far more than what I would have anticipated and we have discussed with Sunil. So it means this course is a success. I mean, in that sense at least. So this course will be up, as already we have uploaded 9 videos to the YouTube channel. So please do share as many as you can and share with your friends or something, this thing. And if we can arrange other courses, we'll definitely let you guys know. Thank you. Sunil, all yours.
Thanks, Sudipta, and thanks to IIT Gandhinagar for organizing this. And thank you all for coming for this final lecture. And I can tell you that it's a good day for me because I'm really glad that I don't have to do this anymore. It's been a pleasure, but also a bit time consuming. So today we'll wrap up by first one thing which belongs to last lecture, which I need to define now, which is called isometry. And then today we'll discuss basically some more properties. So some properties that differential forms have when we introduce a metric. So until now, as you saw, differential forms were things that didn't need a metric to introduce, but we can do things with them in the presence of a metric, which are new. And one of the things we can do with them is to integrate forms on manifolds. And we'll see that the normal integration that we think of, multivariable integration, is sort of a special case of that. Okay, and then I'll end there. Okay, so what is isometry? So let's remember that we've defined a bunch of equivalence relations, not a bunch, just a few. One was for topological spaces, and the equivalence relation was called homeomorphism. Okay, and it was basically a map which was continuous in both directions with respect to the topological definition of continuity, which is that inverse image of open sets is always of an open set is always an open set. Okay, for differentiable manifolds, there was a further equivalence relation, which was called diffeomorphism. And a diffeomorphism is, first of all, a homeomorphism. But secondly, as a map, it's not just it's not just continuous in both directions, it's actually differentiable in both directions. And that's possible to define because a differentiable manifold allows you to differentiate any map, any function on that manifold using charts. Okay, so with homeomorphism, we partition all topological spaces into distinct ones. If two topological spaces are homeomorphic, then they are the same, and we are just working with different descriptions of them. As spaces intrinsically, as topological spaces, they are the same. Similarly, for diffeomorphism, if two differentiable manifolds are diffeomorphic, then they are the same as differentiable manifolds. And now we have the third and last equivalence relation, and this is for Riemannian manifolds. And as you may have guessed, so the first of all, the relation is called isometry. But actually, just like diffeomorphism was a homeomorphism with extra properties, isometry will be a diffeomorphism with extra properties. So isometry is diffeomorphism that preserves the metric. As simple as that, but we need to spell out what it means exactly to preserve the metric. So let's recall that x, y in a product on if x and y are two tangent vectors, then the inner product in the metric G is G mu nu, X mu, Y nu. Okay. Now, when we say preserve the metric, we should have a way of, supposing we have one manifold here and the other here, M and N, both are manifolds of the same dimension. They have to be of the same dimension because they are diffeomorphic to each other. So there's a diffeomorphism, okay, phi. I'll keep calling it phi. It's a homeomorphism, but it's also a diffeomorphism. It's differentiable. And now, I given two vectors x and y. So let me assume that I'm given a metric on M, given G on M. So what do we mean by preserves the metric? It should be possible, if there is such a diffeomorphism, to define a metric starting with this one, to define a metric on the other manifold N, and we define it using the concept of differential map. Now, I think I talked about differential map. I'm a little vague in my mind whether I did, but whether I did or not, I'll do it again now. That given phi from M to N, there is a map phi star called the differential map, which takes me from the tangent space on M to the tangent space on N. Okay, how does this work? So the map phi from M to N just takes a point. Let's say this point in M goes to this point, and it's just a point-to-point map. Okay, but phi star has to do something more. It has to take a tangent vector in M to a tangent vector in N. Now, the way we do this is to notice the following. Suppose if X is a tangent vector, so I can just use simpler notation. If X is a tangent vector in M, so it's in TPM, then phi star X in TPN is defined by phi star X on a function. So the function will be from N to, let's say, real numbers, is the same as X on F composed with phi. What does this mean? Well, I'm given X because it's a tangent vector on the first manifold M. At the same time, if I have a function F on N, then I also have a function F composed with phi on M. How does it work? If F is, so it's easy to see from this diagram, phi takes me from M to N, and F takes me from N to real numbers, and therefore I have a map to real numbers, which is nothing but F composed with phi, which says use phi to go from M to N, then use F to go from N to R. At the end, you've gone from M to R. So F composed with phi is a function on M. Okay, so X is a given tangent vector. F composed with phi is a function on M. So X on this is well defined. That's what X is, a tangent vector on M. So it acts on functions F composed with phi. Now we declare that the action of phi star X on the original function is the same as the action of X on this pulled back function. Okay. Now, since this defines the action of phi star X on every possible function F on the second manifold N, therefore phi star X is defined. So this defines this is the differential map. Okay. So the differential map gives me a unique tangent vector on N starting from a given tangent vector on M. Okay, so now we can easily give a meaning to this statement, preserves the metric. Okay, it simply means that the inner product between two tangent vectors in the metric G is, one second, let me write this, yeah. Is defined to be, or is rather, yeah, is mapped like this to phi star Yeah, good. So we are given a metric G on M, let me call it GM, and we are given a metric G on N. Okay, so both are Riemannian manifolds. That's when there can be an isometry. So it's a diffeomorphism that preserves the metric. That means the metric G on M and the metric G on N should be the same. But of course, they're not literally the same because M and N are in principle different manifolds. So we have to say what same means. And what it means is that the inner product between tangent vectors on M in this metric GM is the same as the inner product between the differential map image of those tangent vectors in Gn. Okay, so if these two things are equal, that's a comparison which says that the metrics are the same. Okay. In words, if I took two tangent vectors and found their inner product in my given metric, or I took them to the other manifold using the differential map and found their inner product using the metric there, if both are the same, then I can say that the metric on the first and second manifold is the same. This is the definition of it. Okay, you may ask, why don't I write GM equals GN? Because it doesn't have any meaning. GM is a metric on M, GN is a metric on N. There is no rule to compare metrics on two different spaces because I might be given those spaces with different charts and all kinds of things. The rule is exactly this. They do their job of providing inner product on the tangent space in the same way on the two manifolds. So that's what, so if this is true, then this is the statement of isometry. Now, before I move on, a very, very important conceptual and very simple point, which is only for the students who might be having a little struggle with this subject. Let's consider a sphere S2. Now, what we intuitively understand as a sphere. Okay, so first of all, what do we understand it to be? It's a topological space. You can define that space by embedding this thing in R3 and using the relative topology. Okay, so it has the connectedness of a two-sphere. So it has the following properties: connectedness, that we assume because we have to build our manifold on a topological space. So we assume that it has the connectedness property. By the way, connectedness doesn't mean whether it's connected or not. Sorry, connectedness is not the right word. It has the continuity structure. So that's what I was trying to say. Continuity concept, you know, topological space has a built into it a definition of continuity. So we assume that definition of continuity corresponds to the relative topology of S2 in R3 as an example, or we build it up in some other way. Okay. Now, then we put a differentiable. Once we have a topological space, then we put a differentiable structure on it. And it so happens there's a theorem that there's a unique differentiable structure on S2. I've mentioned before that this is not true for higher spheres. There are some where it's unique, some are not unique, but on S2 it's unique, fortunately. That means that as a differentiable manifold, every S2 is the same. And what is same? Diffeomorphic. As a differentiable manifold. But remember, we haven't yet introduced a metric. One of the most challenging things for most of you in this course was to realize that often we haven't introduced something, then you can't talk of that thing. Your intuition wants to talk of everything about S2 at once. Okay, but mathematical formalism requires us to introduce the structures one by one. So we made it a topological space by a definition of continuity. Then we made it a differentiable manifold by a definition of differentiable structure. And so far, it's just unique. Okay. Now, we can put different metrics on the differentiable manifold, on the same differentiable manifold S2, And now I can draw a picture which will be familiar to you. In one of those metrics, it will look round. In another of those metrics, it will look like this. In a third metric, it will look as if it has a little bulge somewhere. Okay. In a fourth metric, it may look like this. Notice that it always has the same surface structure as the original one. Okay. And all the different things I'm drawing are actually different metrics on the same differentiable manifold. Okay. Now, of course, there's one more ingredient, unfortunately, to complicate this discussion. What I'm drawing is not just the metric on the manifold, but also how the manifold is embedded in our three-dimensional space. These are supposed to be pictures which give you a suggestion of a solid in 3 dimensions. So that has one more piece of data, which is the embedding in 3-dimensional space. Okay, but what you can see is that if I took this first perfectly round sphere. So this is a very standard thing and goes by the name of round sphere. Okay, the round sphere has a metric which looks the same everywhere. Okay, so the distance between 2 points on this round sphere will be the same if I translate those 2 points all over. And in fact, the isometries of this round sphere are what you could have guessed without doing any calculation. Take the sphere and spin it on the vertical axis. That motion is an isometry. Okay, take it and spin it on a horizontal axis, that's an isometry. Take it and spin it on the other horizontal axis, that's also an isometry. These are all isometries, and they are all maps from the manifold to itself, viewed as a differentiable manifold, where the metric is preserved. Okay, but clearly, if I have 2 points here and I translate them here, the metric is going to tell us something different. Because, right, the neighborhood, I mean, the interval between these, the shortest distance between these, which the metric will determine, may not correspond to the shortest distance between the same points moved somewhere else. Okay, so there's no isometry. A figure like this, which looks very irregular, typically will have no isometry at all. It will just be irregular, and that's the end of it. So spaces with isometry are very symmetric. Spaces without isometry are very asymmetric. Okay, so I hope one message that has gone home, which I labored quite hard in this mini course to communicate, is that it's not the topology, it's not the differentiable structure, it's the Riemannian metric which makes one space as we see it, as we imagine it, different from another. Okay, and that's very important because when a geometer says S2, you need to be sure whether it's S2 as a differentiable manifold, then it's unique. Okay, then all these are the same. And these drawings have no meaning because these drawings are supposed to suggest some metric. Okay, or otherwise we're talking as a Riemannian manifold, then these are different. Okay, so that concludes last time's lecture actually. And today we are going to start by talking about integration of differential forms. And for that, there's a very important and interesting set of concepts here, one of which is the volume form, and the associated concept is Hodge Dual. And the nice thing you'll see is that a metric, the presence of a metric allows us to discuss these things. So we finished discussing differential forms a couple of lectures back, but we only said those things which you can say when there's no metric. Now we are saying those things which additionally you can say when there is a metric, but there'll be metric dependent statements. Okay, so again, in your mind, it should be clear that today everything will be metric dependent, also last time, but earlier things were metric independent. Okay, so good. The first thing to define here is, recall that we had defined frames E upper A. These were actually not frames, these were the dual frames. E A mu, dx mu. So these were one forms. Okay. Now, what if I take, so how many of them are there? A ranges over 1 to n, where n is the dimension of the manifold. So let me consider the wedge product, E1 wedge, E2 up to En. I've taken all the frames and wedged them in order from 1 to n. Okay, so I'll get an n form. That's by definition. It won't be 0 despite the antisymmetry of wedge product, because the coefficient function is actually, so it's different. E1 and E2 are different frames, right? They are A equals 1 and A equals 2 in this example. So they're not the same. So even though they are wedged with each other, that result isn't 0. Okay, so this is an N form. Now, there's a nice, so we'll call it lambda. It'll be very useful to us, and it has a name. It's called the volume form of the manifold. And we'll see that the volume form enables us to do a lot of things. Now, just speaking very technically, it's possible to introduce a volume form without introducing a metric. So people talk about that, but that's, in the formal direction of mathematics. But for us, we first introduce a metric and it gives us this volume form. Okay, now there's a small problem with this volume form, which is that it depends on putting all these things in a certain order. And if I put them in any other order, I may have a different sign. And the problem now is that ON transformations of the frames that right, that the frames can undergo ON transformations, otherwise known as Lorentz transformations in pseudo-Riemannian case, can reverse their orientation. So this is a problem. One example is very simple. Take X, Y, and Z and perform the ON transformation -1, -1, -1. X, Y, and Z all go to minus themselves. Then you'll get X, Y, and Z. And now you will find that this is no longer a right-handed frame. This one is right-handed. So going from X to Y with the thumb rule, the thumb points towards Z. But here going from X to Y with the thumb rule, the thumb points this way, but Z is pointing the other way. So it's the opposite. So this is, if the first was a right-handed frame, this other one is a left-handed frame. Okay, now this won't do, because in that case, the volume form gets ambiguous. If I can keep changing the sign of it, then it's not a well-defined form. Okay, so for this, we restrict to SON frame rotations. Then the volume form will be well defined. But when can I restrict to SON? SON, as you may know, means determinant of the orthogonal matrix is +1. It's not -1. So then this matrix gets ruled out. Its determinant is -1. But we can consistently do that only on an orientable manifold. I defined orientable manifold some time back. And so this is possible only on an orientable manifold. And so from now on, we are going to restrict our attention to orientable manifolds. So we can't define a volume form in a meaningful way on a Mobius strip. You might be able to define some two-valued thing, but you can't use it for integrating, as I'm planning to do. Now, there's some intuition here. You know that the integral of a function, just take a function of one variable. I have limits minus something to some a to b, integral a to b dx f of x. If I interchange the limits a and b, then I get minus the same integral. Okay, so for the integral to be meaningful as a number, I should have a clear idea in my mind what is the order in which the limits are put. Okay, for example, if the function is integrated along the real axis, then I should have in my mind that x goes from minus to plus infinity. If somebody else comes along and makes x go from plus to minus infinity, I'll just get the opposite answer. So the meaning, my answer won't have a meaning. Okay, this is an example of the fact that we need orientation to define integration. So it's not surprising that we need an orientable manifold. So we are going to restrict to that. And within that, we are going to restrict to only SON frame rotations. Now, the nice thing is that the volume form, so first of all, what does EA do under the orthogonal group? It goes into OAB, EB. So this is a orthogonal rotation or it's a Lorentz transformation, depending whether you are Riemannian or pseudo-Riemannian. So OAB element of On. Supposing we allow it first to be an On, then it's easy to show that this volume form I just defined, lambda under this same rotation goes to det of O lambda. Sorry, small lambda. So for SON, which is the case we are considering, lambda is invariant. So it's an SON invariant. It's invariant under my choice of frames, with the restriction that I'm not allowed to reverse the orientation of frames. So my volume form is SON invariant. Okay. So this is good. And now we can rewrite it in various interesting ways. So first of all, the definition, as I said, was E1 wedge, E2 wedge up to En. Now we can expand this by writing this as E1, let's see, E1 mu1, E2 mu2 up to En mu n, dx mu1 wedge up to dx mu n. This is, oops, something terrible happened. I have no idea why. Yeah. Okay. Yeah. So this is obvious because we just use the definition of the dual frames E. Each dual frame is a one form, so I wrote it as a one form. Okay. But now this has some interesting properties. One of them, which follows from anti-symmetrization. So notice that I have n distinct vectors here, and this thing anti-symmetrizes all of them. And it's an easy exercise, and you can try it for small dimensions. You can try it for n equals 2 or 3 and convince yourself. This is the same as determinant of E times dx1 wedge dx2 wedge up to dxn. Now see the difference between this line and this line. In this line, I've written it in terms of the dual frames. In this line, I've written it in terms of coordinates. Okay, and it's not the same because det E is a function of x. The det of this these matrices. So the matrices are E A mu. So the each E is E A mu dx mu. So det as matrices is what comes over here. And because we haven't said anything special about these orthonormal frames, their determinant as matrices will vary all over the manifold. Not only that, we actually know that determinant of the metric G in any given coordinates is the square of det E. Why? Because we proved this relation last time that G mu nu is equal to E A mu, capital E A nu, and a few more relations which tell us, yeah, this is, I think, correct. But okay, I don't remember how I wrote the relation last time. No, I think that's not how, no, this is not right at all. It is actually E A nu. Exactly. So G mu nu is this. Now from this, as a matrix, G is the transpose of some matrix multiplied by itself. So therefore, det G is automatically det E squared. You know that if I have a matrix is a square of another matrix, then det is square. Okay, so this is true. Okay, so therefore, this can also be written root det G dx1 wedge dx2 wedge up to dxn. Now, some of you are looking at this and saying, aha, we know that there's a prescription, which we learned in general relativity textbooks, that when I want to perform an integral over the manifold, I should write root G d for x. Well, this is the derivation, if you like. It comes from the fact that the volume form is the wedge product of dual frames, and then by simple manipulations, that comes into this form as root G and then the product of the individual coordinates. They're still wedged, so it's still not root G, D, and X. It's an N form, actually. This is an N form. So don't yet rush to connect it with the integral that you know. That will come in 5 minutes or 10. Okay, good. Very good. Okay, so we've done that. Now we've written this volume form in a few different ways. So this is again lambda, the volume form. I'm just going on rewriting it in different ways. Okay, now here's another way to write it, which is going to be very useful. Introduce the famous epsilon symbol. You must have seen this symbol in the context of 3 dimensions, epsilon ijk. And the important thing is it has a meaning on an n-dimensional manifold. Epsilon I1 up to In has a meaning. So here is epsilon mu1 up to mu n is defined as 0 if any mu I is equal to mu j. It's equal to +1 if this mu1 up to mu n is an even permutation of 1, 2 up to n. And it's equal to -1 if this mu1 up to mu n is an odd permutation. Just like in 3 dimensions, except in 3 dimensions, we often say cyclic permutation. Here, don't use the word cyclic in general because it doesn't always work. It's not about cyclic, it's about even. Even means the number of pairs I have to permute to go from 1, 2, 3 up to n to mu1, mu2, mu3 up to mu n. Okay, so 1, 2, 3, 4, for example, if that's an even permutation because there's no permutation, then 1, 2, 4, 3 is an odd permutation. Okay, but 2, 1, 4, 3 is again an even permutation, like that. Okay, now in terms of that, we can write, in terms of this, we can write the volume form as root det g over n factorial epsilon mu1 up to mu n dx mu1 wedge up to dx mu n. What did we do? Well, we already had written it in terms of root det g and then the coordinates dx1 up to dxn. This is the same except for overcounting. The important thing is mu1 up to mu n have to be distinct. They were distinct here in this case. Now here what we do is we let them be distinct but not ordered from 1 to n. We allow all orderings. How many orderings are there of n numbers? N factorial. Okay, so we allow all n factorial orderings, but this takes care of the fact that if the ordering is odd, that means this is an odd permutation of 1 to n, then this thing would have a minus sign relative to the original one, relative to this one. But in that case, epsilon also has a minus sign to compensate. The result is that this much is a sum of n factorial copies of the same thing. That cancels this n factorial and we are back to the original form this. But this form somehow had 1, 2, 3 explicitly written out, and this form has hidden that by introducing a new symbol called the epsilon symbol. It's something similar to a tensor, but it's not exactly a tensor, and it has many interesting properties. Before I go further, let me also say that we define epsilon mu1 up to mu n as what we get by taking g mu1 nu1 up to g mu n nu n on the lowered one. But notice that this one had components plus and minus 1. Okay, plus and minus 1 only. But then all these are functions of x. So there's no sense in which this one is plus or minus 1. This is actually a non-trivial function of x. So don't ever get into that. On a non-trivial manifold, epsilon with all lower indices is plus or minus 1. Epsilon with upper indices can't be plus or minus 1. The upper indices were produced by acting with g. This is actually g inverse, by the way, because it's g with upper indices. So this epsilon with upper indices has a non-trivial x dependence, and it's not as simple as it was in flat space. In flat space, either one up or down didn't matter too much. You might at most get a sign wrong. Another thing to realize is here I've raised all the indices, but I can also raise some of the indices of epsilon and not all if I feel like. So I'll use those now. And now we are in a position to define a very interesting operation called the Hodge dual. So for that, let me recall a property which I probably didn't emphasize about differential forms. So I'm not really recalling it. I'm probably telling you for the first time. Zero form is a function. one form is omega mu dx mu. So there are n possible components, right? Because mu ranges from 1 to n. But a function has only one component. Okay, let's see how many components a two form has. Omega mu nu dx mu wedge dx nu. Now, because of the antisymmetry, this has n minus 1 by 2 components, or more abstractly, n choose 2, which I'll write like this, binomial coefficient. Then 3 form has n choose 3, etc., up to n form. Now the n form, the maximum one you can have, has n choose n coefficients, which is back to 1. So you know this property of binomial coefficients. You get 1, n choose 2, n choose 3, and after some point, the numbers start decreasing again. Okay. For example, if n was 4, you would get the famous 1, 4, 6, 4, 1. Okay. So in particular, this tells us that a P form and an n minus P form have the same number of independent components, because n choose P is the same as n choose n minus P, just an identity in binomial coefficients. Okay. So there should be some relation between P forms and n minus P forms. And in particular, I'll now tell you that with this epsilon symbol, or equivalently with the volume form, I can define an n minus P form given any P form. And that's called the Hodge dual. So the Hodge dual is given a P form. And let's write the P form first. The P form is omega equals omega mu 1 up to mu P. And this is on an n-dimensional manifold where n is generically larger than or equal to P. Otherwise, this doesn't even make sense. Okay. If you want an example, think of a 2 form on a 3 manifold or a 4 manifold. Okay, then star omega has the following definition. It has many different definitions. One of them, which I'll give you first because it's the easiest one to apply concretely. You multiply always by this factor, root det g, and divide by n minus p factorial. Then you bring in the epsilon symbol, and you give that epsilon symbol, let's see. No, don't first bring in the epsilon symbol. First, you write the components, omega mu 1 up to mu p of the original form. Now you introduce an epsilon symbol which contracts away all these indices. But of course, there is no such epsilon symbol with p components on an n-dimensional manifold. The epsilon symbol only makes sense if it has n indices. So there are still many indices left. So we'll write them here. Mu p minus 1 up to mu p plus 1, plus 1 up to mu n. Okay, so this is a partially raised epsilon symbol where I started with all lower indices and I raised the first p indices using the metric. All right, and finally, I multiply this with dx mu p plus 1 wedge up to dx mu n. Don't worry if this is getting too complicated. We'll do a simple example in a few seconds. Okay, you can see that indices are properly contracted because the omega indices, this is the original form, is contracted with the first p indices of epsilon. But precisely by its nature, if epsilon has p of its indices contracted away, then it has n minus p of its indices free. And those ones are free to contract with n minus p dx's. And this whole thing manifestly is a n minus p form. But its independent information is precisely the same as that of omega, because its independent information is only this. All the other information like this and this are all determined knowing the manifold. Okay. If this is a dynamical object, for example, it could be an electric field or some other physical vector or tensor or something, then, sorry, if this is a dynamical object, this is the same object just described in a dual language. It's just an n minus p form. Okay. Now, the reason to put these prefactors in this, so this motivation is not very difficult to see, because what we are trying to do is to dualize a p component object into an n minus p component object using epsilon. That's basically what we've done. Okay. So this is an n minus p form, this one. Now we have the property that star of star omega is back to omega. And if I didn't put this root det g, I wouldn't have that property. Now I can prove it for you, and I have the proof written down here, but I don't have time. So I'll leave it to you as an exercise, and I'll also pause there a couple of questions. But the important thing for you to realize is that in this formula, you see there are all these upper components of epsilon. Okay. Now, because of raising many indices of epsilon, we get factors of det g to the inverse. And when we do star twice, we get root det g twice. So it cancels the det g to the inverse such that this can be true without any factors of g. Okay. Meanwhile, this gets cancelled because this epsilon contractions always overcount. They count many things, many permutations. And if you count all the permutations, you get this factor which cancels this. So that's just in words why it's true. But better than words is an example. And what you'll realize is that this is an example you've always known. So this example is n equals 3. A three-dimensional manifold like space, Euclidean signature. So here, and it's flat, so root det g is not there at all. I can raise and lower indices freely. Still, it's interesting to see. So first of all, the volume form is dx1 wedge dx2 wedge dx3. Or in more conventional notation, dx wedge dy wedge dz. Still a 3 form. It's always a form of the dimension number equal to the dimension of the manifold. Okay. Now, what is star of the one form dx1 is just dx2 wedge dx3. What is star of the two form dx1 wedge dx2 is just dx3. Okay. It's always the one that isn't there. If it was a curved manifold, there would be something more to put in, and for that you would have to use this epsilon definition. Okay, but let's look in fact at more general vectors. So let's suppose I have a vector or rather a one form. Now I'll take my one form to be maybe A and B. So A equals A. Because I'm working in three-dimensional space, I'm going to call it AI dxi. Whenever it's intended to be space, I use these indices, summed from 1 to 3. B is bi dxi. These are two independent unknown one forms, ai of x, bi of x on my space. Okay. Now, what is A wedge B? Perhaps I should have done this last time. By definition, it is ai bj dxi wedge dxj. It's a two form. Okay. This is also equal to half aibj minus ajbi. Because this anti-symmetrization is automatically done because of the thing that's being multiplied, which is already anti-symmetric. So this is a two form which is made of two vectors. Now in school, they don't teach you that the wedge product of two vectors is a two form, but they teach you the next step, which seems more easy. What is the star of A wedge B? So it's the dual of this two form. Now, if you work out the formula for the dual of this two form, you'll find that this is nothing but epsilon. So let me write it in the way I wrote the previous formula. It is ai bj epsilon ij k dxk. Okay. Now, I think that I haven't made a mistake and this is correct, including factors, but it could, maybe I have made a mistake and this is half. I'm not totally sure if this should have a half or not. If somebody knows, they should tell me. So let's see, let's go back to the definition. I should multiply by root g, but that's 1 in this case because I'm in flat space. N is 3 and P is 2. So I don't have anything to divide by. So this is actually correct. Then I have to write the components, which are just AI, Bj. That's this thing. And then I have to put the epsilon and finally that. So this is star of A cross B. Now, this K being up or down doesn't matter anymore because we are in flat space. So what is epsilon ij k ai bj? So this is another vector which I can call ck, and this equation is basically the cross product A cross B equals C. As simple as that. So the moral of this story, and you know that the components of A cross B are the one component is A2 B3 minus A3 B2. Well, it's all in this formula. Okay, so the Hodge dual of the wedge product of two one-forms is the cross product of those two one-forms in 3 dimensions only. Notice that the Hodge dual of the wedge product of two one-forms is going to be an n minus 2 form in n dimensions. Only when n is 3, it's a 1 form. Okay, and really speaking, this teaches us something which can help you if you are thinking about geometry in 3 dimensions. You see, the real meaning of cross product is that it's related to a particular plane. That means you have a vector, you have another vector. The cross product is associated to the plane spanned by the two vectors. And if they are parallel, there's no plane spanned by them. And also the cross product is 0. Okay. Now, only in 3 dimensions, the normal to a plane is a line. Okay. And that's why this 2 form A wedge B can be mapped into a 1 form C. However, this 1 form contains this curious factor of epsilon ijk, and we saw that under improper rotations, that is under O3 rotations which change the orientation of the frames, epsilon changes sign. So ck changes sign under a frame change oppositely to the way a normal vector would behave. And therefore, it's called a pseudo vector. Now you know why A cross B is called a pseudo vector. It's because it's really not a vector. It's a 2 form. And to get the vector C, you'd have to take a dual. But when you take the Hodge dual, you introduce an epsilon. So this thing is often called a pseudo vector in physics. And it's because of this. All the blame goes on epsilon. So Hodge dual always has that property. Okay, so I hope you found this amusing because it's something we knew in high school, but actually it's arrived at using dual frames and their wedge products. This also tells you why there's no cross product for 4-dimensional vectors. In GR, nobody tells you there's a cross product. Okay, you can't take the 4 velocity or the 4 momentum and cross it with another one to get a vector. What you do when you cross it is that you will get a second rank tensor. And if it's anti-symmetrized, then you can dualize it into a different second rank tensor with the same information. That will be the 2-form dual of P1 wedge P2, where P1 and P2 are some 4 momentum. So you can do all that, but the cross product is special to 3D. Yeah. Can we treat EA mu dx mu as an infinitesimal? No, we cannot. There's no technical explanation. I emphasize that that dx over here is not to be understood as an infinitesimal, but just as a basis. So it's an n form, it's just a formal structure. Now, to connect that formal structure to the infinitesimal is something we are about to do. So again, just wait till I do it. Yeah. It's small g, right? Although it's just notation. Well, yeah, sometimes, yeah, you're right. It's small g, sorry. Shouldn't star omega have factors of -1 coming from a possible negative signature metric? Yes, that is true. But when I write formulae, and if there's any ambiguity, the formulae are always for Euclidean signature metric. So that star depend. Otherwise, I would have to give you a bunch of formulae depending on the dimension of space-time and all that. So there could be a sign, but in Euclidean signature, thank you. So I should perhaps have said this in Euclidean signature. Thank you. Good question. Okay. Now, at somewhat lightning speed, we have to go through the concept of integration on manifolds. But, it's not very difficult now that we have a volume form. And I think it's very illuminating. I think you're going to like this. Okay. So first, let's now consider the Hodge dual of the volume form. So I took the trouble to introduce a volume form. So the volume form is lambda equals E1 wedge up to En. And it's also root G dx1 wedge up to dxn. Let's go over the definition again. We had equivalent definitions. So root G upon n factorial, excuse me. No. Here there was, I'm looking for this formula. This formula just has a root G and then dx1 wedge up to dxn. So I'm using that version of the volume form. Okay. Now, let me ask the question, what is the dual of this? So the dual of this will have another the dual of this will have another root G and an n factorial, right? It will have no n factorial because the dual, as per this formula, is the dual formula. I think it's here. Yeah. It's root G over n minus p factorial. So p is n in this case. So 0 factorial, that's just 1. And because n minus p is 0, that is p is equal to n. So the dual of an n form is a 0 form, otherwise just known as a function. Okay. So the dual is really just det G. Okay, it's that simple. Now, okay, I have written something here which I'm a bit confused about. Root det G. Maybe I didn't want the dual. I just wanted the function itself. Yeah, I don't need the dual just now, so let's not write it. Okay. So now we want to integrate some function. So now, okay, good. So this is the volume form. That's fine. Now we want to integrate on an n manifold. And let's pose the question how we are going to do it. So here's the manifold. And what do we know about it? Well, it's a differentiable manifold, so it has charts. And the charts have overlaps and some nice properties. Now, in principle, this set of charts could be infinite. It could be an infinite cover. So if I'm given an arbitrary set of charts, it could be infinite. So here's the manifold M. Here are some charts. So each of these is assumed to be mapped homeomorphically to a subset of Euclidean space, and that associates coordinates to this chart. Then on the overlap of two charts, I have to use the usual rules to go from one to the other. Okay, change of coordinate system. Okay, now in principle could be infinitely many charts, but in practice, let me take a compact manifold. Do you remember the definition of compact manifold? It's defined by saying that every open cover admits a finite subcover. Okay, and that's now we are going to use that because these charts form an open cover, obviously, because the union of these charts is the whole manifold. Okay, and each chart is an open set. But now I can, this implies that there's always a finite subcover And this is very good because I'm going to use this finite subcover. So that says that without further assumptions, I can restrict myself to a finite set of charts which cover the whole manifold. Okay, so we'll work with the finite subcover. And let's give it a name. So finite cover in short. The idea is that I can choose a finite cover. If you choose an infinite cover, I can choose a finite subcover by the compactness of the manifold. So we work with a finite cover and we call it M alpha, phi alpha. Actually, M was not a nice term. I think my notation in the book has been a bit inconsistent. So maybe U alpha is better. It's an open set and phi is the homeomorphism to some subspace of Euclidean space. Okay, and remember that phi alpha of U alpha is a subset of Rn. That's exactly how a chart works. Good. Now, good. Just give me a second. Yeah. So now the point is the following. I can integrate. So let me define the integral. So now let me take. Okay. So let me explain a few things. Okay. So we are going to integrate an n form on an n manifold. Now you may say, I don't really want to do that. In physics, I want to integrate functions over the manifold, but you'd be wrong. We are really not integrating functions over the manifold. We don't know it, but we are integrating n forms over the manifold. And because we are doing it using the dual zero form to that n form, we get an extra factor of root g, and that's the root dead g, which comes in the integration measure from the physics point of view. Okay, so here I want to integrate an arbitrary n form on an n manifold. So the first rule is we can't integrate anything on a manifold except an n form. You can't integrate a function, one form, two form, three form, except an n form. So if the manifold is 7-dimensional, you can only integrate 7 forms. That's the first rule. Okay, so it's the only thing that's actually well defined mathematically. And integrating of functions is defined secondarily through integrating the n forms by a Hodge duality. If you wanted to integrate a 2 form, you could integrate it through a 2-dimensional submanifold of that manifold. That you can do, but in that case, the submanifold would have to be a 2-dimensional submanifold. I hope that point is clear. Okay, so first we'll define this, and this will in particular define also integrals over submanifolds, because the same definition can just be applied to the submanifold. Good. So let's take an arbitrary n form omega, which as I already said is mu omega mu1 up to mu n, dx mu1 wedge up to dx mu n. Okay, now define a of x equals epsilon mu1 to mu n, omega mu1 to mu n. This I can do. This is not exactly the Hodge dual. What's missing in the Hodge dual is the factor root dead g. Okay, so I'm not doing that. I'm just defining ax to be this. The important point is that it's a single function. It's not a proper scalar because of that missing root dead g, but it's a single function which carries all the information of the n form. Again, no surprise, because an n form being fully anti-symmetrized over n indices only really has 1 degree of freedom, and a of x is that degree of freedom. Okay, now I'll define the integral of omega on the chart u alpha. And notice that when we write this, we don't specify any coordinate system. This is a coordinate system independent definition, but the definition is given in terms of a coordinate system. Okay, I mean, this left side is coordinate independent. I'll now give you the definition in some coordinates, and then we'll see that if I change coordinates, the definition changes to the same form in the other coordinates. Therefore, the quantity is coordinate independent. So I'll emphasize that here. It's coordinate independent, and it's understood to be the integral of a form over a chart. However, I haven't integrated it over the whole manifold, only over one chart. Okay, so it will actually be coordinate independent if I remain in the same open set U alpha, because I haven't even defined the integral on another open set. So we'll come to that next. So the definition of this is, take this function a of x and carry out the integration on phi alpha of U alpha, which, as you know, is an open set of Rn. And in Rn, we'll simply take this function and multiply it by dnx as a multivariable integral and perform the integral over x1, x2, x3 up to xn. Okay, so this side is the Euclidean thing, which is well defined because we know how to integrate a function of many variables over all the variables. It's like integrating dx, it's like integrating, I don't know, a charge density over space, integral d3x rho of x. It's like that. This is well defined, but I'm claiming backwards that this defines the integral of an n form on a chart of the manifold. And now my job is to patch up all such integrals to get the integral of the n form on the whole manifold, and this is not so easy. Let's see why. So patch these up to get integral omega on m. That's what our goal is. Once we get that, we are done. Okay. Why is it not so easy? First of all, before I patch them up, I had one thing to show you, the coordinate independence of this. Now, the interesting thing is that if I go from xi to yi of x, dnx is not invariant. I think you know this. Why? Because the integration measure on n variables changes by a Jacobian. dnx goes to dny, which is equal to the Jacobian determinant dyi by dxj dnx. So this factor is not coordinate independent. However, now something nice happens because of this factor. This factor, if you remember, is not exactly the Hodge dual of omega, but it's the Hodge dual with a root g removed. Okay, because root g is removed, it actually transforms a of x, can be shown to go to a prime of y, which is Jacobian determinant del xj by del yi a of x. It's precisely because that root g was removed. And so in the product of these two things, you see that this product is equal to this product because it's equal to this product, and these two things neatly cancel. These two Jacobians are equal and opposite of each other. So this is the, so it's independent of change of coordinates for a given chart. So in other words, if I went from U alpha with a homeomorphism phi alpha, which gave me the x coordinates, to U alpha, the same U alpha with a different homeomorphism psi, which gave me the y coordinates, then it's independent of that. So I've achieved one thing, at least I have a coordinate independent definition for a particular patch or open set of the manifold. Now I have to do what I said here, which is to patch it up. So let's do the patching. For the patching, we need one auxiliary construction, which is kind of cute, and it's called a partition of unity. Now, very unfortunately, in my book, I've called this partition E alpha, but I would like to reserve E for frames and dual frames. So here I'm going to call it F alpha. So F alpha of X is a family of differentiable functions on M, one for each patch of the atlas, one for each chart of the atlas. And remember, this is an atlas with finitely many charts, because every open cover had a finite subcover. So I have finitely many functions F alpha. Now let me give them the following set of properties. Then only there'll be a partition of unity. First of all, I said F alpha is C infinity. It's different, continuous and differentiable. Okay, now the value of f alpha ranges between 0 and 1 only for each alpha and all x in u alpha. So this is a function which only takes the range of values 0 to 1. That 0 to 1, not 0 and 1. So it can be any number between 0 and 1, including 0 and 1, but it can't be negative and it can't be greater than 1 anywhere. Okay, so it's strictly non-negative and strictly bounded above by 1. Okay, the third property is that E alpha of x is 0 if x is not contained in the chart U alpha. Let's try to understand that by drawing a picture. Here's the manifold, and here are two charts, U alpha and U beta. Okay, now there's an overlap, and that's very important. Let me explain why we are doing this partition of unity. You see, I can define the integral of a function on a patch. So you would think that I can add up the contribution from all patches and get the integration of the function on the manifold. Why will that fail? Precisely because of overlaps like this. Because on this overlap, the integral of the function as I defined it on patch U alpha will get some contribution, but I'll get also a contribution because the same thing is also in the patch U beta, so I'll double count those points. Okay, that's no good. So you may say, good, I want disjoint charts covering the manifold. Then it will all work. Yes, you're right. But disjoint charts can't be open sets in the sense of topology that we understand it. The manifold is not disconnected. It's connected, so it can't be a union of disjoint charts. So overlaps are compulsory. So here we are stuck with the problem that overlap of charts is compulsory. But then if I add up the integral of the function over each chart, I'll be double counting the integral on all overlaps, and that will give me a wrong answer. That's where this partition is helping me. So in this partition, E alpha is a function that's supported only on its open set. So for example, in this picture, the region where E alpha is non-zero is this region only. The region where E beta is non-zero is this region only. Outside their given regions, they just vanish. Okay, so that's one property. And the fourth property, which makes it a partition of unity, is that if I sum over all the charts E alpha of x, even though each of them is a function of x, the answer is a constant function 1. This means that at every point, whether that point is in an overlap of charts or not, the sum over these E's is 1. I think every single point of the manifold, this is true. Okay, so now the fun comes, because now what we can do is to define the integral of the whole n form over the manifold as the summation over charts integral over the particular chart U alpha, E alpha of x times omega. So omega is an n form. E alpha is a plane function. Okay, so E alpha times omega is again an n form, different one. Okay, but now what happens is that this function is confined. This function has support only inside the chart alpha. Is 0 outside that. Okay, and because it has support on, so this omega is non-zero everywhere on the manifold in general. Once I multiply it by E alpha, then by this property, it vanishes outside the chart alpha. Because of that, I can integrate it over the chart U alpha. I could not have integrated omega. Well, I guess no. That's not true. It's this, okay, because of that, I can still integrate it over the chart U alpha. But now I sum up over all these contributions. And now see what happens on the overlap of two charts. On the overlap of two charts, I'll get a contribution from E alpha omega and also from E beta omega, where the alpha and beta are two charts that overlap. Okay, but if there are no other charts overlapping those two, then E alpha plus E beta in that region is 1. Okay, so I don't count anything extra. I get part of my contribution from the chart alpha, part from the chart beta. If you want a pictorial description, it's like this. On this overlap, what happens is over here, we have this restriction that the functions E alpha and E beta have to add up to 1. So neither of them can be equal to 1. Okay, because they are strictly between 0 and 1 and they have to add up to 1. Okay, so we don't care what they are. As long as they are differentiable, we don't care what they are. We don't even have to ask what they are unless we want to actually do something more concrete. In the abstract definition, we just assume that they exist. Okay, and what will happen is E alpha at every point x will have some value less than 1 and E beta will have some value less than 1. Okay, but they are adjusted so that the total value of those two is 1. You might be tempted actually to take this summation inside. But in fact, it's not, it can't take it inside because the integral is over this region. So this whole integral has a dependence on alpha from this as well as this. Okay, so this is the definition of integral of defines integral of n form omega over n manifold n. And what it does is that it introduces a partition of unity. For each partition of unity, it integrates E alpha times the given form over the chart, and then it sums over everything. And you can prove formally, or you can try to prove informally, that this gives me the correct contribution that it should have in every overlap of charts. If there's a chart which doesn't overlap with any other, then of course, this restriction tells me that the corresponding E alpha is exactly 1 in that region. Okay. If there's any part of the manifold where there's a chart which doesn't overlap with any other chart, then how can this be true? It can only be true if E alpha for that chart is 1 in that region. Okay, so only on overlaps, E alpha will fall below 1, E beta will rise to some value greater than 0, but the sum of the two of them will be 1. On an overlap of 3 charts, the sum of 3 E alphas will be 1. Okay, so that's how it works. Now it's very abstract, admittedly, but one can actually prove, and I've given this proof in the book, that can prove that the answer, this one, is independent of the partition of unity. So if I choose a set of, sorry. Somebody should have screamed at me long ago. I started calling them E alpha. I'm really sorry. These are all F alpha. I think you guessed it, but still. Deep apologies. Is the partition of unity, so it should be F alpha. F alpha. Okay. So it's independent of the partition of unity. So if I have a partition F alpha and you give me a partition F prime alpha, it's actually very cute proof. You can introduce 1 equals summation of your F primes, and then you can take F prime inside the integral, and then you can take F outside. It's a very nice and simple proof. And it basically shows you that this is also equal to summation alpha, same charts, different partition of unity. For any other partition, you can prove this. Okay, so I'm done with most things, and there's only one topic remaining, and that's will occupy the last 15 minutes, and that's called the Laplacian. We'll learn some fun things there, but first let me see if there are questions. Yeah. Thank you, Tanmay. I meant F and not E. I should have seen this earlier. Yeah. In integrating, would integrating over disjoint unions not work? Yeah, it would not work. There's no such thing as a disjoint union of charts that covers a connected manifold. And it's the reason you're suggesting this is that you forgot the definition of connected topological space. It's connected if it's not a disjoint union of open sets. Is that clear? So no disjoint union of charts are possible. Think of this way. Try to think of the real line as a disjoint union of charts. You can't, right? Because each chart is an open set. Each open set is an open interval or a union of open intervals. But I cannot cover my real line with open intervals unless they are overlapping. And this is the beauty of topology. You have to understand that this is not an inconvenience. This is exactly the point. That topology gives you a sense of open set, And these open sets have the property they can cover things that you want covered, but they'll always overlap. They won't be able to cover things disjointly, and if they do, the things will be less interesting. Because, for example, if if open sets covered a manifold disjointly, the manifold would be disconnected. Now I'd be back to considering each separate sub part of it as a sub manifold, and then try to apply my working to that. So disconnected manifolds are not interesting, not because they can't exist, but because they are just combinations of connected manifolds, two or more. Yeah. Why did we have to use forms in defining integration? I'll come to that. Why did we require the manifold to be compact? Yeah, I told you that. It's because I wanted to make, I can give you a one-line answer. I wanted this alpha to be finite. If the manifold is not compact, then alpha is not finite, need not be finite, because I may be given an infinite cover and it may not have an open subcover. Okay, so for example, if I was working with R4, which has exotic differentiable structures, you might give me an open cover which doesn't have a finite subcover. It's not compact anyway, and then this won't work. However, that's not to say that integration can't be done on those manifolds. It can, but you have to give up compact and you have to go with something a little more general called paracompact. Okay, now paracompact is something that is not necessarily compact, but it says that every open cover admits a locally finite refinement. I've discussed this in the book. You can look it up there. So it's not to say that this thing I'm doing cannot be done on a curved general a non-compact manifold with a metric. It can, just that I'm not doing it here. Yeah. Why did we have to use forms in defining integration? I'll explain that. It's okay. Maybe I didn't explain it, but I think the key point, maybe I didn't harp on it enough, was the patchwise definition of integral, which was this one. For this integral to be coordinate invariant, I could not use a function. A cannot be a function. If A is a function, that's the same as a scalar, then A doesn't change under change of coordinates, but dnx does change under change of coordinates by the Jacobian, this factor. So therefore, the result I would get would be not invariant under change of coordinates, and it would be useless. It wouldn't be a property of the manifold. Now, you can use two languages. One language, you can say that I'm going to, and this is the physics language, you can say this is equal to A of x upon root g dnx. Okay. Now, this thing is an ordinary function. A is not a function, but A upon root g is an ordinary function, and root g dnx is invariant under change of coordinates. Okay, so because of this, so A of x, remember the correct, anyway, so this is the point. So if you try to integrate a function on a manifold using the same logic, you'll end up having to introduce a factor root g artificially in your integration process. You can do it. The point is that this process is actually the integral of a form. That's why it's working like this. Okay. The statement that we have to introduce root g here and divide by root g here to get invariant quantities is basically the same as the statement that the Hodge dual of the function is what is really being integrated. And you see, there's no loss in this because the Hodge dual of a function is an n form, but an n form is also a function. It's just a function with different powers of root g. That's what you have to appreciate. So if you don't like the statement that we are integrating forms over manifolds in an invariant way, you could say that we are integrating functions, but our rule says to put root det g whenever we do this integration. Actually, it's the same thing. Content-wise, in practice, it's the same thing. But conceptually, it's not the same thing. Conceptually, what we really are saying, actually, if you look at examples, you'll understand it better. There's a natural sense in which I can integrate a two form over a two manifold. Let me remind you that in physics, we talk of magnetic flux. Now, if you really think of magnetism in this language, you'll realize that the magnetic field B is a two-form D of A. I think I already mentioned this. So B is B mu nu dx mu wedge dx nu, and it's just del mu A nu dx mu wedge dx nu. So it's a two-form. Again, why do we in physics, why are we taught that B is a vector? It's actually not a vector, it's a pseudo vector. Why? Same old thing, our friend Epsilon symbol converts the two form B in space into a one form pointing in the perpendicular direction. That's because in 4 dimensions, we have a picture in our mind of what is the 3-dimensional submanifold of space. So in that one, we can perform this epsilon, which is like a Hodge dual, and get the magnetic field to be a vector with an odd inversion property. And that's how we'd like to do it. But this is more natural. Now, the flux, the magnetic flux of the magnetic field, as you know, is the integral of B over an area. What is an area? It's a 2-manifold. Okay. Now, see, this is exactly what I've just defined for you. This is a 2-form. This is a 2-manifold. So now you're assured that this makes geometric sense. Now, of course, if you just want to integrate B dot dA over a disk or some two surface in flat space, you won't go wrong because there's no metric. The metric is unity. So that root G factor doesn't matter. But if you try to integrate B dot dA in a space with a metric which is non-trivial. So for example, if you're working on surface of a sphere or on 3-sphere or near a black hole or anything, then your definition won't work unless you're careful about root G. But this definition is absolutely clear on any space. It actually is defined independent of the coordinate system manifestly and is the integral of the 2-form on the 2-manifold. If you keep pursuing, go back to your physics. Thank you. I'm glad you got it. If you go back to your physics, you'll also see that for Ampere's law, we integrate A dot dl. What is that? Integration of a one-form A, the vector potential, over a circle, over a loop, which is a 1-manifold. Okay. So you will see that naturally we keep integrating things over the manifold that they sort of naturally belong to. Now you may say, well, I integrate del dot E over whole of space. Del dot E is not a 3-form, looks more like a 0-form, it's a scalar. But actually, del dot E is nothing but the exterior derivative of the 2-form F0i. So again, it's naturally a 3-form. So I don't have time, but if you reformulate electromagnetism, you'll see that electromagnetism knew all this perfectly well. And with that, since I don't want to go way over time, I still have my 7 minutes. I have to define a few things. Elaborate a bit on chronology. No time, sorry. Stress again on importance of frames. Yeah, no time. Achal, no, thank you. Good questions, but no time. Okay, so Laplacian. Okay. Now, there are some fun questions that you could have asked, but none of you did ask. It's interesting how the number of questions has gone down as the course progressed, but this would have been the time to ask interesting questions, such as with a metric, we have an inner product on Tp of M. Do we get by duality an inner product on T star P of M? Well, we do, but it's a little unexpected and non-trivial and very useful. We do. We get an inner product on differential forms as well. Yes. And what's the inner product? Take alpha and beta. Let them both be P forms. They have to be of the same form dimension. The natural inner product is to take alpha, wedge it with the star of beta. Now notice this is a P form and this is an N minus P form. What is the wedge product of a P and N minus P form? It's an N form. What can I do with an N form? Integrate it over the whole manifold. So you see that we've got the integration over the manifold allows me to define an inner product between any two forms of any dimension as long as both have the same dimension. Same form number, not dimension is just a word. Yeah. Okay. And it can be shown that alpha beta is symmetric. It's not manifest because we chose to take alpha wedge star of beta. We could have also chosen beta wedge star of alpha. Turns out those two are the same. Up to a possible sign, and those signs will take care of themselves because these differential forms come with those dx things. Okay. Oh, by the way, I forgot to make one comment. This is the point in the whole discussion when the dx of differential forms got associated to the dx of infinitesimals. This dnx is really infinitesimal in the sense of integration measure, the dx of integral fx dx. On this side, it just had its differential forms, dx mu1 wedge, dx mu2, etc. Okay, but on this side, it was just an abstract differential form integrated on a given Riemannian manifold. And on this side, we introduced the usual Riemannian, the usual coordinate measure on flat space, because Euclidean space is something where we know how to do integration on regions. So this is where finally the dx of that notation gets related to this. But don't be too quick in doing that. On the left side, there's a wedge product of the abstract dx's. On the right side, this is not a wedge product. This is just dnx. It's the infinity, x to x plus dx, y to y plus dy, z to z plus dz. That little cube is the volume of that little cube. It's the calculus dnx. And this is the point where the two get associated. Till that time, they were not associated and they were abstract. Coming back to where we were, this thing is symmetric. We can also show that if I have the same form with itself, this is greater than or equal to 0 in Euclidean. Otherwise, I don't know for sure that this is true. Okay, now a very interesting thing called the very interesting definition. It's called the adjoint. So given a form, given alpha, which is a P form, the adjoint denoted delta alpha. Again, this is not an infinitesimal, it's just an operation acting on alpha, is a P minus 1 form, one lower dimension, defined by inner product of alpha d beta is delta alpha beta. Now let's be careful. For this left side to make sense, this is a P form. Therefore, this whole thing has to be a P form. Therefore, beta has to be a P minus 1 form, so that its D of it can be a P form. Okay, so beta is a P minus 1 form, and delta alpha is that P minus 1 form whose inner product with any beta is alpha with d beta. Now you'll immediately notice that delta acting on a 0 form just can't work. So that's fine, because delta acting on a 0 form would have been a minus 1 form. But then on the left side, we can't set up this relationship at all. So there's no minus 1 form beta. So therefore, delta alpha just has to be 0. Okay. It's parallel to the statement that if I have an n form, then d of that is 0. D of an n form is 0, and maybe I should have stressed it, because the n form is already fully anti-symmetrized. So it has already one dx1, dx2 up to dxn, all anti-symmetrized. If I put another one, it has to be one of the first n, because there are only n dimensions. And so by that anti-symmetry, it will be 0. So the same logic. Okay, so this is the adjoint. Okay, and now we can use the definition. So the left side, as we know, is defined as alpha wedge star d beta. Okay. Now, what do we have on the right side? Well, if you go to components carefully, you will find that there's a relation between this quantity on the left and minus 1 to the n times p. This is the product of the numbers n and p. N is the dimension of the manifold, and p is the dimension of the form alpha, times integral of star D star alpha wedge beta. This is an identity which can be proved. What is this thing? This thing is, take alpha, which is a P form. First take its dual, so it's n minus P form. Now take its D, so it's n minus P plus 1 form. Now take its star. Now it's a P minus 1 form. Okay, so this actually tells us that up to a sign, delta is the same as star D star. So it's pretty obvious when you think about it. This is three operations. First, take the Hodge dual. That increases the form dimension. Then that gives flips the form dimension from P to n minus P. Then take D, that increases the form dimension by 1. And then again flip from P to n minus P. The end result is a P minus 1 form. Okay, so this is a nice operator, and actually there's a very nice application of this. I wish I could have told you in more detail. Delta on a one form omega I dxi turns out to be equal to 1 by root g del I root g omega upper I, where that upper I is raised by the metric. And notice this is a one form, this is a function. Okay, and it may not be obvious, but if you know GR, you'll realize that this thing is actually general coordinate invariant, and it's nothing but the generalization of the divergence del dot. So del I omega I would be divergence of a 3 vector, for example, but in this notation, it's actually acts by delta. Okay, and divergence, since it takes a P form to a P minus 1 form, it will take a 1 form to a scalar, and that's exactly what del dot E is. So if you want to write del dot E in form notation, then the correct thing is to write E as EI dxi, and then act with the delta operator on it, and that will work on any manifold. Okay, and now we are almost done. So first of all, recall that d squared omega was 0. On any form omega, if I do d twice, that is curl of curl, I get 0. And this implies that delta squared on omega is also 0. Proof is very simple. Delta squared omega is star d star d star omega. But these two stars combine into nothing because star of star is what it was. So it's star d squared star omega, and d squared is 0. So delta squared is 0. Okay, which is good because we know that there's nothing like divergence over divergence. Okay, by the way, delta is a divergence even on n forms. We know divergence only acting on one forms, but the divergence defined through delta will act even on any p form of any dimension. Good. Okay, now the last step, the Laplacian on a manifold is defined as capital delta is equal to d plus delta the whole squared. It's very cute. It says take the exterior derivative and the adjoint, add them, even though they do very different things. D raises and delta lowers the form dimension, but still add them as operators and square. Now the square is quite simple. It has d squared, which is 0, plus delta squared, also 0, plus d delta plus delta d. So actually it's just equal to d delta plus delta d. So the Laplacian takes a form, lowers it with delta and raises it back with d, back to the same dimension, plus another term where it raises it with d and then lowers it with delta. Okay, and these two give different contributions in general. One of them may be 0 sometimes, but the sum is the Laplacian. Okay, and this is the generalization of del squared to a general manifold. You can also give nice definition in terms of coordinates. So it's 1 by root g. It's also equal to 1 by root g del I root g del g I j del j whatever. I may or may not have written this right, but anyway, this is also what it is. But this is the kind of nice way to write it, because it tells you in differential form language what it's doing. And a very good line on which to close this mini course is the Hodge decomposition theorem, which says that any differential form is really beautiful. This is on compact manifolds. By the way, this time it really does need a compact manifold without any boundary. Any differential form, P form, can be uniquely decomposed as omega equals d of something else plus delta of something else plus gamma, where gamma is a solution of Laplace equation. So every form has three parts which can be found uniquely. One is the d of something else. This goes by the name of exact. One is the adjoint of that, that is its delta of something else. So beta has to be one form dimension higher. And after you've removed these two, the remaining gamma is a solution of Laplacian on gamma is 0. It's a very beautiful theorem. And if you see, we implicitly apply it in physics all the time when we talk about uniqueness of solutions to Laplace equation or Poisson equation. So I think that's a good point to stop. Thank you very much. It's 5:37, a little bit over time, but I see that I don't have any questions, which is really good news. Yeah, over.
Okay. Okay, so thanks a lot, Sunil.
Thank you.
I hope you can hear me.
I can.
And I also thank everybody who has still survived. And we hope that we'll be able to continue this program. So this is the second program after Krishnendu's course. This is the second course, and we are already trying to plan a third course. So all of you, please keep in touch, and you can always look at the YouTube of our channel where all the videos will be uploaded.